techniques that will maintain the consistency between different cores when a data is updated in a private cache. As mentioned in our previous lecture, we explained that how an inconsistency occurs. How inconsistencies occur when the data is updated in one private cache, while the same copy of the data exists in another private cache. Now let's assume like these are two cores which has a copy of a data and both are in shared state. When the data is modified here and it's not modified here, so this core will have an inconsistent data. This core will have an inconsistent data. So what's the method to maintain consistency in the previous examples? Whenever there is a write to a cache line, this core will notify all other cache. There are also different states of this cache. One was a private state and another was a state. And there was also coherence directory. And all these information was maintained in a coherence directory. In coherence directory, which information, whether the copy, the data that is maintained in a cache, whether it is in a private mode or in shared mode. And there is also some sharing vector, that which of the cores has a copy of the data. Okay? Now, but maintaining coherence will become more complicated when the number of cores will increase. Now let's assume if we have an 8-core system or a 16-core system. So in that case, when we have an 8-core system or a 16-core system, so in that case, it will be difficult to maintain consistency. It will be difficult to maintain consistency. And the consistency problem will exist when the consistency problem will become more and more complicated if you increase the number of cores. Okay, now let's say we have 16 cores, and now this cores copy the data and it informs all the other cores. So maintaining this coherence message from this core to all cores will require huge network overhead. Okay, one approach to solve this problem is a non-cacheable memory. Solve this problem is a non-cacheable. In a non-cacheable memory, this concept is very simple. Now we have a memory map. And each core is assigned some private portion and some shared portion. So it means that this address space is only dedicated for core 0. This address space is dedicated for core 1, this address space is dedicated for core 2, and this address space is dedicated for core 3. If core 2 wants to read the data from this region, it will not be allowed. If core 3 wants to read the data from this region, will it be allowed or not? It will not be allowed. But now we have a shared space, and this shared data is shared between all cores. So it means that whenever core 0 requests the data that belongs to this address space, it will be cached within a private cache. When core 1 addresses some data that belongs to this address space, it will be cached in this private cache. But when core 0 wants to access this data, it will not be cached at all. It means it is non-cacheable. So whenever core 0 wants to read the data from the memory, it will read the data from here, but it will not go to the cache. Core 0 will directly access it from main memory. Okay, now if core 0 wants to write the data, it will write the data from memory. So each of the core will have a consistent view of the memory. And because this data, okay, the problem in the previous example was existed. Now exact example. Now let's say this is a core 0, okay, and this data is 55. This data is 55. So what? This 55 will be read from this memory and it will go to the cache. This value. The problem was arise when this 55 was written. Which data was written? Now if the same data, now let's assume we have this shared data. Okay, now not 50, let's assume we have this shared data, 55. Core 0 access this data and if it brings it into the private cache 55. And it's a read operation, not a problem. Again, core 1 reads this data and now it's also 55. Okay, now if core 0 write this data and now the new data is 76 and this core 1 wants to read the new data, what's its new value? 76. That is 76, but it will get a stale data that is inconsistent or consistent? Inconsistent. That is inconsistent. So to avoid this problem, now we have a memory map, and for this memory map, some address space is allocated for each core. This address space is allocated for core 0. This address space is allocated for core 1. This for core 2 and core 3. This address space will contain the data only relevant to core 0, and this will the data relevant to core 1. Now if core 1 wants to access this address space, he can access it, but if core 0 wants to access this address space, he will not be allowed to access this address space. Okay? Okay. Now I will explain this with an example. Now let's assume each of you has a mobile phone, and that mobile phone is actually private to each of you individual, and that is private, and basically you can only see. But if there is a television in a common room, so all of you are watching the same television. So actually that television is then shared. And that is shared among all the students. So now actually this region of the memory will contain the private data that is relevant to core 0, private data relevant to core 1, private data relevant to core 2, private data relevant to core 3. And now this is a shared data. Okay, now if this core 0 wants to access this data from the shared data, it will not be cached at all. That's the reason it's called as non-cacheable memory. So this region is cacheable or non-cacheable?
Non-cacheable.
Non-cacheable. So if core 0 wants to access this data, now let's assume this is a read operation. So core 0 will read it. Read the data. Okay? But it will not be brought into the private cache of core 0. If core 0 wants to write the data, then it will modify it in the main memory. And because this data is shared, so each of the core will have a consistent view of the data. Because the data is now placed at only how many locations? Single location. In the previous example, in the consistency problem was actually each of the core had some private cache, and that it will cache the data, and the problem of consistency arose when the data belongs to the private cache of different cores, and one core writes the data. Then the consistency problem arises. आप समझ आई बात है? ठीक है? Okay. Now this is one way to achieve consistency. Okay.
सर इस केस में भी तो इनकंसिस्टेंसी है. फॉर एग्जांपल फर्स्ट आपका जो कोर है इसने डेटा रीड किया उसी
कौन से कोर में?
सर
कौन से कोर में डेटा रीड किया? कोर 0 ने
55 रीड किया.
किधर से रीड किया?
मेन मेमोरी से.
शेयर्ड लोकेशन. तो शेयर्ड तो कैश में नहीं आएगा.
कैश में नहीं आएगा, ठीक है सर. लेकिन उसने उसके मॉडिफाई करने से पहले ही अगर कोर 1 ने रीड कर लिया है तो उसने तो पुराना डेटा रीड किया ना.
देखिए जब जाहिर बात है, जब आप देखें आपको याद होगा कि in operating system there is one mechanism that's called as Semaphore.
Yes.
In Semaphore, whenever you want to access some shared data and it is a critical data, तो जब आप उस डेटा को एक्सेस करते तो आप उसको लॉक कर देते या नहीं करते? ठीक है? तो basically there are two type of operation. When there is a read operation, it will not be locked. When there is a write operation, before performing a write operation, it will lock get element. When it's locked, so it means that let's say if it say that now it has read 55, not a problem. But if it wants to write this location, first it will lock the data. When it will lock the data, so actually the lock will be then 1. When other cores wants to read this data, say that now it's locked. Who has locked this data? Core 0. So when core 0 will release the lock, then another core can access it. So actually now there are two mechanisms. One is the hardware mechanism and another is the software mechanism. So actually this will be maintained by the operating system. So actually in operating system you may have studied, आप लोगों ने पढ़ा होगा computer science में operating system में. कि operating system में when operating system wants to share some critical data, ठीक है, and that data is critical and that data is shared between different cores. Okay, so when there are multiple cores, so there is when some code wants to write some data, so it will apply a lock. Okay, this is the okay. Another mechanism is called as write through policy. So now we also have now this is the mechanism in which we have only private cache. There is no shared cache. Now if we introduce a shared cache here, and then main memory. Okay, so in that case you can then have a copy of this data into the shared cache, because if the cache is shared, it means you have now a consistent view of the memory. Now you have a consistent, and every of the core will first access the shared cache. If it is not found here, then it will go to the main memory. So now even this shared data can be cached in a shared cache, but this shared data cannot be shared in a private cache. Now why it can be shared in a shared cache? It can be shared in a shared cache because this shared cache is shared among all cores, and all cores will have a single view of the data, not multiple views of data. The problem arises in private is because you have a different views of the data. Some data will be consistent and some data will be inconsistent. So in private, the consistency problem arises when there are private cache. When you have a shared cache, then the consistency problem does not arise. Okay, now there is one approach like now if you have, let's assume if you have many cores, 16 cores or 32 cores, and now you want to maintain the consistency measure across all the cores, it will become more complex. So sometimes now you have different levels of cache hierarchy. One hierarchy can be like this. Now if you can see it. Now you have core 0, core 1, core 2 and core 3. It has private cache, private cache, private cache, private cache. And now you have shared cache. Then you have core 4, core 5, core 6, core 7. You have then private cache, private cache, private cache, and then shared cache. So you can have different levels of cache hierarchy. अच्छा ये भी हो सकता है कि this now we have some clusters now we have some clusters in this cluster and now this cluster. Now if you have if you have a single shared cache, will it be more complex or the system will be simple? It will be more complex. So what can you can also do some clustering. You combine some data and now you can have, for this architecture you may have some view of the memory like this now. Now you have a view of the memory. So this memory will be shared by only core 0 to core 3. This memory will be shared only by core 4 to core 7. This will be updated by core 8 to core 11, and similarly this value from core 12 to core 15. Okay, now maintaining the coherence between these 4 cores will be easy, but maintaining coherence among all 16 cores will be easy or complex?
Complex.
Will be complex. Now, it's easy for it to share the coherence message within these 4 cores. But if you have 16 cores, actually the problem arises now when you have many cores and you have a chip. So actually if one core is located here and one core is located here, so actually the distance between these cores will be very high. So actually the problem arises because of the interconnect latency. Now you have to communicate the message to a far core. Okay, now let's assume if I want to transfer the data from this location to this location, it's a short distance. But if I want to transfer the data from this location to this location, the distance is large. The latency will be large. So actually, if you look at from the electronics perspective, so actually these will be some wires. So now the length of the wire from this end to this end is short. Now if you have many cores, the length of the wire from this core, from this region to be large. So the latency will be large. So actually, then having a cache is not advantageous if you want to maintain some private cache. If you have some private cache, and if you are sharing any cache between multiple cores and all of the cores are sending the request to the same cache, so actually there will be a lot of the shared cache will be inundated by a lot of requests to the same shared cache. So actually there will also create a problem of contention. There will be more contentions, and this not only contention because there will be more requests, but the contention also arises because one core is evicting the data from the other cores. Now let's assume if we have this cache and we have a cache set, okay, and now we have associated use. You have 4, 5, 6, 7, 8. If you are only inserting the cache line from a single application, the contention will be less or more? Or from a single application? Less. But if 8 applications are sending the data to the cache set, there will be more contention. When there will be more contentions, so the cache hit rate will be high or low? The cache hit rate will be low. Because one core, now let's assume if we have these 3 seats and we have data only from one application, so actually you can fill this seat easily. But if there are more and more applications, so it may also happen that one application may be evicting some useful data from another application. This is also a contention arises. So the contention arises when a cache is shared between multiple applications. And it will not only create more traffic, but it will also cause an eviction problem. Okay, and it will decrease the cache hit rate. Another policy to maintain consistency is write-through policy. What is a write-through policy? One was write-back policy and now it's a write-through policy. Now, when we have some data, let's assume this has a tag some data, and now this data is 55. Okay? This core wants to read this data. It will put 55 here. When it wants to read this data, it will be okay. So when it reads the data, its value will be 55. Okay. Now if it writes the data, so it will, when it writes the data, so then it's write the new data to 75. So it is immediately updated here. It is immediately updated here in the shared cache. Okay, now with this 55 and now 55 is also here. Let's say 55 is also here. Now you have a sharing vector. Which of the cores is now accessing it? 1 1 0 0. So when it writes the data 75, so then it will look at the sharing vector. Which of the core is now sharing it? Core 0 and core 1. Who is writing this data? Core 0. So this data will be again written. So this is called as a write-through policy. In the write-through policy, whenever there is a read operation, so for read operation, we will always have a consistent data, no problem. Now let's assume if multiple cores have the same copy of the data, and it's a read operation, so the data is not modified then. When the data is not modified, what does it imply? The data is consistent or inconsistent? Consistent. But when inconsistency will arrive?
Write operation.
When there is a write operation. When there is a write operation from any core, then let's assume this core generate a write operation. But it will inform it will update the main memory or shared cache. It will update the main memory or shared cache. Okay, now when it's updated, it will look at the sharing vector. So what does it imply? Which core is now writing the data? Core 0 is writing the data. Which core has an inconsistent data?
Core 1.
Core 1. So that data will be then overwritten in the private cache now. So this policy is called as write-through policy. In the write-through policy, whenever there is a read operation, so actually it will be read and it will be cached in the private cache of a particular core. But whenever there is a write operation, it will not only be written into the private cache of the private core, but it will also be written into the main memory or shared cache. When it's written in the written into the
Main
memory or shared, it can also be a shared cache. And now we can have a main memory. Okay, now we can have two policies. The policy between this core and this core can be write through, and the policy between the shared cache and the main memory can be
write back.
Write back. In write back policy, we maintain a dirty bit. Achha, let's assume that the same copy of the memory, initial value is now 55. Initial value is now 55. Now its value will be, dirty bit will be 1. The dirty bit will be 1. So whenever this data is evicted from the shared cache, then it will be updated in
main memory.
And basically the consistency problem will not arise because all of the cores will first look into the shared cache between going to the main memory. So all of the cores will have a consistent view of the data in a shared cache. So we can have different policies. So the policy between this shared cache and these private cores is write through, and the policy between the shared cache and the main memory is
write
back. So you can also have between this, you can also have a write through policy. You can also have a write. It depends on the policy that you want to maintain.
लेकिन अगर हमारे पास इंटेंसिव राइट एप्लीकेशन आ जाए तो उसमें तो फिर ये
अगर if the application is write intensive, if the application is write intensive, so actually what is the disadvantage of write through? If you have a write intensive application, so there will be more and more updates, and actually updates to main memory are more costly compared to the updates in the shared cache. So actually you can have a hybrid policy between the shared cache and the private cache. You can have a write through policy, and from the shared cache to the main memory, and basically write back is much better here. Why it is much better? Because all of these cores will first go to the
shared cache.
Okay. So now let's assume, now we assume scenario. We assume scenario in the main memory. Now let's assume the value is 65, some data. Okay, and there is a miss. This is core 0, core 1, core 2 and core 3. Okay, there is a miss in the shared cache. Core 1 has requested it. Core 1 has requested the data. Core 1 has requested which data? 65.
65.
This 65 will be put in
Shared cache.
shared cache. Now what should we do now? We should update the which vector?
Sharing.
Sharing vector. What will be the value of the sharing vector?
0 1
1 0 0. And now with the sharing vector, so actually this 65 will go here.
Yes, sir.
This 65 will go here. Now, in the first case, there was a miss in shared cache. The data is brought from the
Main memory.
main memory and put it in the shared cache, and the sharing vector is updated.
Yes, sir.
Okay? Okay. Now, that bit will be 0 or 1?
20 bit will be 1.
0. It's a read operation.
Read operation.
It's a read operation. So it means miss in the shared cache and it's a read operation. That bit will be 0. After some time, so now we have a read miss by core 1. Read miss by core 1. That if it is 0, sharing vector is this. Now we have read miss by core 3. What will happen? Core 3 will have the same copy of the data. The sharing vector will be updated.
Yes, sir.
What will be the value of sharing vector?
0 1 0 1.
1. That bit will still be 0.
Yes, sir.
Now it has also the copy of the data.
Yes, sir.
Okay. Now,
Sir, why is it read miss by core 3? Read hit नहीं होगा sir? It is shared में.
read miss for a private core perspective.
Private.
This is
core
read
memory.
miss by core 3 private cache.
Private cache.
This is a read miss by core 1 in the private cache and a shared cache.
Shared cache में hit हो गया वो फिर.
And then in this case, shared cache hit. It's a hit in the shared cache, but a miss in the private cache. In the first example, it was both a miss in the
Shared and private.
shared cache and non-private cache. Okay, no problem. The data is now brought here. The data is now brought here. Now, if we have a write hit by core 1, write hit by core 1. Core 1 will write. Now let's assume the new data is 97. The new data is 97. So it will be updated here.
C3 में भी update होना चाहिए. Yes, sir.
And this will be then
In C3
updated. And then the data bit will be
1.
1. And when this data is evicted from the shared cache,
ये main memory भी update होगा.
then manually will be updated. But in the meanwhile, there is a read miss by core 2. Core 2 will see which data? 97. It is consistent or inconsistent?
Consistent.
Consistent. 97. So now what is the new bit? That bit is 1. Now what is the sharing vector?
0 1 1 1.
Okay? Okay?
Yes.
So now in this case, we have used a combination of
Write policy.
write through policy. Write through policy is realized or implemented between the private cache and shared cache, and now we have maintained a write back policy between a
Shared and
shared
main
cache.
memory.
Okay, so when the cache is shared, okay, and there is no private cache, let's assume there are no private cache, will the consistency problem will arise if you use write back policy? Now I will ask these simple kind of questions in my OSTs then. Logical question, logical reasoning question. Now let's assume a scenario. We have these cores, they don't have any private cache. Now we have a shared cache. Assume a scenario, we have 4 cores, they have no private cache, and this cache is shared. And now we are using write back policy for this shared cache. Will consistency problem arises?
No.
No. The consistency problem will not arise. Because in a shared cache, you have now a single copy of the data. When you have a single copy of the data, so the
There is no
consistency will not
need.
arise. The consistency will arise
multiple
when you have some,
multiple copies of the same data.
when you have multiple private cache, and that cache is dedicated to a particular core. And what is the advantage of, actually typically, if you look at this scenario, so actually typically the private cache is very closer to the processor,
Yes.
and it's small, and it's much faster. And the shared cache is typically
Larger.
larger, and it's
Away
slower.
from.
And if you look at the main memory,
It is more larger.
it's even more slower. And then if you look at the hard disk,
So both is slow.
is the slowest. Like if you look at the hierarchy, the memory hierarchy. So now we have the hierarchy. If you look at the pyramids of the hierarchy, and on top of this there were registers, then cache, private cache. Okay, private L. Acha, it's also possible. You can have multiple private cache, L1 cache and then L2 cache, private L1, private L2, and then shared L3, then main memory, and then
Hard drive.
okay. So now I think you have understood right through policy, the complete
Yes, sir.
the complete concept of the right through policy. Now there are two types of policies. One is called as right through with right allocate and right through with no right allocate. So the first policy is right through